Hi again, guys. What I want to talk about today is the concept of relative motion. Now, anytime that we say that something is relative, that means it depends on what your viewpoint is. It's compared to something else, is what relative motion would look like. So the easiest way, I think, to describe this is to think about some examples. So let's say that we have a bus, and I have a person that's on the bus walking down the aisle. Another person is riding on the bus, but not moving compared to the bus. And we've got an observer that's standing on the sidewalk off to the side of the bus. So depending on which observer that we look at, whether it's this person on the side or this person on the bus, the velocities that they see will look very, very different. So for instance, if I think about this observer, could you tell me how fast that the observer watches that bus moving? Well, clearly, if I look at this example, if this bus is driving down the road and their speedometer reads 40 miles per hour, then this observer would see the bus moving at 40 miles per hour in this direction. All right, so they would move this way. But if I think about the bus itself, if the observer is on the bus, how fast would the observer on the bus think the bus is moving? Well, in this case, really, they're surrounded by the bus. And aside from being able to see outside, they really couldn't tell if that bus is traveling at a constant velocity and they couldn't feel an acceleration, they would think the bus wasn't moving at all. So this observer has a different point of view from this one, and it makes a difference in terms of what velocity they would see. Another example is the person who is on the bus but walking down the aisle. If that person is walking towards the back of the bus, if you think about it, their velocity is in this direction, but the bus's velocity is forward. And so from the point of view from this observer outside the bus, if they could see that person, let's pretend we have a crystal clear bus where they could see everything that was going on inside of it, they would see this person moving. But how fast? How fast would that person be moving from this person's point of view? Well, they're on a 40-mile-an-hour bus moving this way, but they're moving in the opposite direction. And so what this person would see is this person moving in this direction at 37 miles an hour. Be sure that makes sense to you. All right, because their velocity was in this direction, but the bus's velocity is in the opposite. What I would have to say from this person's point of view is that I would add those two vectors together, but because this one is moving in the opposite direction of this one, I would take the difference between them. So it's 37. How about this person's point of view? How fast would this person in the aisle be moving from their point of view? Well, because they're moving forward at 40, the same speed as the bus, this person would basically see the aisle walker as walking 3 miles per hour towards them. All right, because their two velocities are both on the same bus that's moving in the same direction, but this one has a speed relative to the bus speed. From his point of view, he's moving 3 miles per hour. From his point of view, he's moving 37 miles per hour that direction. How fast is this guy moving from his point of view? Well, he'd be moving the same speed as the bus, which is 40 miles per hour in that direction. Is he moving from his point of view? He would be. Right? He would be. He'd be moving 40 miles per hour in that direction as he comes through in the bus. So again, your point of view often is going to determine your velocity. Right? Your point of view is going to determine your relative velocity compared to all the objects that are around you. Another application of relative motion is when we look at spaceflight. So, for instance, one question that I would ask is, why do we launch rockets? When we launch, the United States at least, when we launch rockets, we always launch them from Florida. And whenever they launch from Florida, they always fly out over the Atlantic Ocean. So why do we do that? It's always the same. Why does Florida get to have the space launches and no one else does? Well, there's a reason, and it's related to relative motion. So we're going to do a close-up here, and I'm going to explain it for you. So in the same way that someone walking on a bus, so if I have a bus that's driving forward at 40 miles an hour, and they're walking towards the front of that bus, if I was outside the bus, if they're walking 3 miles an hour, and the bus is going 40, they would look to me like they were moving, if I was outside of the bus, they'd look like they were moving 43 miles an hour. I can add their two velocities if they're going in the same direction. Rockets are going to use a similar idea with Earth. And for a minute, I want to talk a bit about Earth, and then we'll come back to this. The Earth rotates, and as it rotates, it always rotates in the same direction. So you can see right now, Florida is right here on our globe. And if you think about the sun, we kind of off to the side on the globe. The sun rises first in the east and then later on in the west. And so the Earth then must be spinning, if you can see it, basically the sunlight is going to cover the Earth in the side that's facing the sun. But if the sun is rising in the east and setting in the west, then it must be that it's rotating in this direction, towards the east, you could say. So why is it a benefit for us to launch rockets from way down here in Florida, and they always fly over the Atlantic? Well, number one, if I'm spinning in this direction, and so is all of the air and everything else that's on top of the globe, it's all spinning in this direction. So that means if I launch from Florida and I launch towards the east, not only do I have the speed that my rocket is traveling at, but I also have Earth's speed. And so in order for me to escape from Earth's gravitational pull, we have what's called an escape velocity. And that escape velocity is 11,200 meters per second, really, really fast. Well, the benefit I get is if I go with the spin of Earth, we kind of get a little boost. Earth is kind of like our bus, and the rocket is like that guy walking on the bus. If the rocket goes in the same direction that Earth spins, it gets an extra 1,000 or so miles per hour. Okay? So the reason we fly east is we get a little boost. We get the advantage of getting Earth speed plus the rocket speed. So we don't have to get going quite as fast, all right, to reach that escape velocity. The other reason that we launch from Florida, because you think about it, I could really take off anywhere and fly to the east and I get that benefit. But the other advantage you get is think about how fast you're actually moving. If the Earth's spinning like this, okay, the further north that I get, the slower you're actually moving. This spot right up here, if I go straight to the North Pole, effectively what would happen is every 24 hours, I would just turn in place. Well, I'm not moving very fast if I'm just kind of sitting there and spinning. The further towards the equator you get, the further distance you travel in that 24 hours. And so why do we pick Florida? Number one, the weather's decent. Number two, it allows us to fly out over ocean when we go to the east, which we want to because it gives us a relative speed boost. Number three, though, it's about as far south, as close to the equator as we can get in the United States. And so that means not only are we traveling towards the east, we're traveling more, Florida is traveling towards the east more quickly than, say, Maine is way up here, or Canada is up above that. So it's southernmost, which means faster, and we can take advantage of the ocean safety-wise as we fly towards the east. Again, though, that extra 1,000 miles an hour or so that we get from the Earth's rotation means we don't have to fly quite as fast to get out of Earth's gravitational pull. So I want to talk about one more example. Let's say that you launch a projectile off a moving vehicle. Okay, so you have the projectile launcher with you, and you're on the moving vehicle. How fast is that projectile going to move from the point of view of someone who is standing off to the side watching you drive by? So we actually did this experiment. We set it up and we calculated using our t-shirt cannon that we have, a pneumatic cannon. Projectile launcher sounds better. People get freaked out when you say cannon. So we put a projectile in that and then launched it out of the back of the truck while the truck was rolling forward. Now, what we did first is we figured out how fast that projectile would be moving out of the t-shirt launcher when it was just sitting still. And what we found is that at a particular pressure, this t-shirt launcher would launch that projectile at a speed of 39 miles an hour at a particular pressure. Then what we did is I got in the back and my brother was driving and he just got up to 39 miles an hour, the speed that we knew we were going to launch this at, and then I launched. So what do you think's going to happen? Well, remember what we've done in all of these examples, whether it was the bus, if the bus is going forward and the guy on the bus is walking forward, we would add those two vectors together. If the bus was moving forward, but the guy in the bus was moving towards the back, we'd still add them together, but his velocity would be negative. It would be in the opposite direction. So we would subtract it from there. Well, think about the setup that we have here. This is going to launch this projectile, all right, at 39 miles per hour. But the truck is moving forward at 39 miles per hour. What do you think's going to happen? Well, we got video footage. We're going to go ahead and look at it, and you'll see what happens when you launch out the back at the same velocity that the vehicle is moving forward. So as you might have guessed, it's pretty much what you suspected. If you launch out the back at the same speed that the truck is moving forward, from the point of view of someone on the side watching this, I would add those two vectors, positive 39, negative 39, they'd cancel out, and what you saw was that overall velocity was 0. All right? From my point of view in the back of the truck, it looked like it was moving at 39 miles per hour in the opposite direction. We want to finish off by going through an example. So these are the kinds of problems that you might see when we talk about relative motion. So this question tells us that we have a boat headed north and it's crossing a wide river with a velocity of 10 kilometers per hour relative to the water. The river has a uniform velocity itself of 5 kilometers per hour due east. Determine the boat's velocity with respect to an observer on the shore. All right, so they talk about crossing a wide river. So let's say that these are the riverbanks here. And the boat is going to go across this river due north. So I'm going to go ahead and get a compass rose in here, north, south, west, east. This boat is going to try to go directly across the river with a particular velocity. And so just like the question on the bus just like Earth spinning and being able to add the vector, the speed vector of Earth and the speed vector of the rocket to get a higher speed overall, we can do the exact same thing with here, or with this question. We're simply going to add the vectors together. So I have a single vector that is going to go due north, all right? And we know from this question that the magnitude of this vector is 10 kilometers per hour, okay? And to that vector, I'm going to add the velocity of the river itself. The river is going 5 kilometers per hour towards the east. And so to the head of the boat's vector, I'm going to add the tail of the river's vector. So we know that this represents 5 kilometers per hour. Okay? So what is the velocity of the boat from the point of view of someone who's standing off to the side over here? All we do is connect the very beginning to the very end. And if I figure out what that is, I've got the relative velocity from his point of view of that boat. All right? How are we going to do this? Well, we know that this is due north and that is due east. And by definition, those two, north and east, are at right angles to each other. So we have a right triangle where we want to know the hypotenuse. And we know the two sides. This is a job for Pythagorean theorem. So I would say that c squared equals a squared plus b squared. If I substitute in some numbers, a we'll say is 10 kilometers per hour. I'm going to square that. B is 5. Move off to the side. And we're going to square that. So c squared then, 10 squared is going to be 100. 5 squared is going to be 25. If I add those two together, I get 125 kilometers squared per hour squared. And we take the square root of both sides to get our answer. If we do that, the number that I come out with is that velocity along that course is going to be 11.18. When you take the square root, you also take the square root of the units. So that would be kilometers per hour. Really, when I look at this, the 5 only had 3 sig figs. So I should round this to 11.2. So that is my speed. That's the speed this boat will be moving, okay, along that track. I still need to get the direction. Now, remember with vectors, when we determine direction, we always go with the angle from where we started. So I'm really interested in what that angle is right there. Because I know the adjacent side and the opposite side, we're going to use tangent here. So I would say that tangent theta, tangent of that angle is going to equal the opposite side, which is 5. Over the adjacent side, which is 10. My units, of course, will cancel. And really, we don't want tangent theta, we want theta. So in the end, this is going to be inverse tangent. So my angle is going to be equal to inverse tan of 5 over 10, which is 0.5. If you do that, let me get out of the way so you can actually see this a little bit better. If you do that work, then what you're going to find is that you get 26.6 degrees. Now, how would I describe that? Well, I've gone towards the east from north. So what I would say is this is 26.6 degrees east of north. There's the second part to my answer. So the combination of the speed and the direction gives me a velocity for that boat. So again, on these questions, you guys, you're going to have essentially two velocities. And you're just going to take those two velocity vectors and add them together the way that we do with vectors, which is to connect them head to tail. All right, both of them head to tail. Draw a resultant from the very beginning to the very end, and then go about doing your mathematical procedures. Usually, we're talking about Pythagorean and then inverse tangent to get your answers. All right, you guys are going to get an assignment on this. This is relative motion, where we add and sometimes subtract velocity vectors. We'll see you guys next time.